This video presents an edge computing application used as input use case that provides sensors virtualization in the IoT context. The service provider creates the application template by using the input dashboard to define the service chain of the application and specify which modules will be connected to the user personal network or, if needed, traditional backend networks. The dashboard is the same as OpenStack for ease of usage, but some extensions have been applied to allow the definition of input-specific parameters. The service provider interacts with the dashboard to create a new image that will be made available for the creation of a personal service. In this case, the created image is a historical data cache that is used to store the data retrieved from home sensors and to expose them on request. The service provider browses for the image file, selects and adds it. Then, he specifies the architecture, in this case x86-64 for a 64-bit architecture, and creates the image. The service provider can view and manage the network from the Network Topology tab, which at this stage shows only the personal network, and begins adding virtual machines instances to compose the personal service. The first service instance to be created is the historical data cache. First, the service provider selects the correct image among the list of available ones. Then, the desired flavor is selected. The historical data cache virtual machine is associated to the personal network. The definition of a proximity class and the possibility of making a virtual machine multi-user are some of the extended service requirements that have been added to the input dashboard. This particular instance is not shared and has the proximity class set to 6. The second instance added to the service is the Cape the Wolf virtual machine, which is used to contain the virtual objects that will be associated with the sensor of the user. Cape the Wolf is the platform as a service adopted in the input architecture. It provides RESTful APIs that can rely on the HTTP protocol for management purposes. The Cape the Wolf virtual machine is bound to the personal network as well. Its proximity class is set to 1. The stringent proximity will require the virtual object instances bound to the sensors of a user to be migrated upon his movement, as will be shown in the final step of this video. After the service chain configuration is finished, the service is made available to the users for subscription. When a user subscribes to the Virtual Collector service, the OpenVolcano interface of the telco operator displays the occurred subscription by means of a created user and related multi-center personal network. In this use case, we consider the presence of 3 sensors, 2 located in the user's home and 1 in his car. The map on the right shows the data center in which the virtual home gateway instance has been placed. The user can subscribe to the personal cloud services by using the Virtual Home Gateway web interface offered by OpenWRT. In this case, we can see the subscription to the IoT service of which we have just seen the template creation. Upon completed subscription, the placement of the three virtual objects representing the sensors is shown on the data center map. The foreground chart shows statistics on the status of the data center resources. The IP addresses of the interfaces of the virtual machines and additional smart objects that are connected to the user personal network are automatically assigned by the DHCP. The user can access the historical data cache dashboard to read data recorded by his two home sensors. The Add Device button allows to insert the device name in order to bind the virtual object to the device. By selecting the device, the user can easily retrieve information specifying the Lightweight M2M standard fields for resource definition from the left panel of the dashboard, which represent the device instance if available, and the sensor value. The user can set an observer in order to have a periodical data retrieval from a device to be consulted. The dashboard allows to do that with the Add Observer button. Observation requests are sent to the virtual object, which periodically sends data to the historical data cache to be consulted when desired through the dashboard. Using the dashboard, the user can easily connect new devices to the personal network, read data from the devices, and consult historical data stored in the database. The dashboard offers the additional capability of overwriting a value or more values into a specific resource or object instance. The virtual object then in charge of forwarding the request to the device and storing value. The second home sensor is added and bound to a virtual object. The same steps as before are repeated to read data from the device, consult historical data stored in the database, and write new data. The virtual object communicates via REST API, so it can be managed by any applications able to perform HTTP requests. In this case, the Postman REST client application is used for your IoT device management. Once a virtual object is bound to a device endpoint as shown in the previous step, it is possible to use Postman, for example, to get the address of a resource or additional information regarding its status. Requests can be also performed to retrieve real-time data coming from the devices that are bound to the virtual objects. In order to show how the IoT use case performs in mobility, on the top left we can see the LTE PC web interface, while the three OpenFlow maps show the physical network topology with the 4 points of presence and the logical view of two data centers. The one on the left initially hosts the home gateway, the historical data cache and the virtual object bound to the three sensor instances, while the one on the right hosts the second virtual object. The HTTP call in the terminal displays the three virtual object instances bound to the input CD2 virtual machine. We trigger the migration of a virtual instance by physically moving one of the sensors from being closer to the node B on the left to the one on the right. A handover request is detected by the S1 AP monitoring VNF, and when completed, it is also shown in the messages displayed by the PC web interface. As soon as the handover is completed, the new position of the user, the mobile sensor, and related center are updated in the physical view. At the same time, the corresponding instance is disconnected from the original KP Wolf virtual machine and bound to the one in data center 0. A new HTTP call shows the occurred binding of the mobile sensor instance to the second virtual object.